In this example, I'm going to go over the kind of circuit analysis we can do if we have only one source, which is this case. Here, the question is at what rate is thermal energy, which is power, generated in 20 ohms resistor. The 20 ohms resistor is this one. Alright, so this voltage is given to be 20 volts. It's given here. Alright, so how am I going to find the power? Now you have to remember the way we evaluate the power. We have two kinds of elements in our circuit. The active element is the source. So the power of the source, P, let's call it S. Since it does not have resistance, it is an ideal source. So just the EMF, if given, times the current going through that EMF. So if I can find the current going through this EMF, then I have access to the power delivered by the source, produced by the source. And this is the kind of power I can evaluate across this source. Now, I can also evaluate the power dissipated. That power produced by the source will be consumed and then converted into heat. So heat is energy per time, the rate is power. So the power across R, like so, can be evaluated in three ways. If you know the voltage across R times I, this is one way. Or if you know the resistance, which is the case here, times I squared. And therefore, the best way to evaluate the power everywhere, 20, 30, anywhere, is to find the current, because the current squared times that resistance is the power. Another way is if you have the voltage across that resistor, then V squared over R. So we have all choices, right? So the question is, what is the power across this resistor here? All right. Now we can add more questions. So what's the point here? What is the approach? The idea is to reduce this circuit to a very simple one when you have only the source and the equivalent resistance. Here you don't really need Kirchhoff because you have only one source. You can contract the circuit and extend it later if you wish. So going from this part, let me use the color here. So this is the given circuit. The next I have 30 and 30 and 30. They are in parallel. You can see this point is the same. And therefore, I'm going to combine all these together as one equivalent, which is reciprocal 30, 30, all together reciprocal is 10 ohms. Now this 10 ohms here stands here in series with the rest. You can see 10 plus 20, 30, 40, 70 ohms. We combine them together if they're in series. We combine the reciprocal if they're parallel. Now, the equivalent to this circuit is this one. I have the source 20 volt, did not change, and the equivalent resistance. Now, the current I, using Ohm's law, is the voltage over R. This is true if you have only one resistor. But in my case, I have the EMF, the voltage is called EMF for the source, and R is not just a simple R, it's a combination, it's R equivalent. This is the same equation, Ohm's law, adjusted to this configuration. So this is 20 volt, and the equivalent is 70. So let's do the math. What is this? How many amps? So 20 divided by 70. All right, it is 0.28. Let's say 6 amps. All right. So this is the current going through. You have to be careful. This is the current leaving the source, the total current produced. Okay, this is the current here, almost 0.3 ohms. So it is going through here. If you go back, this is the source leaving, current leaving the source, and this is also the current coming. It is the same current, and therefore I can find the power across the 20. The R is 20 ohms, and the total current coming going through 20, which is also leaving, times 0, 2, 8, 6 altogether squared. Alright, so let's evaluate this. This is squared equal times 20 equal. So I have 1.63. 1.63 watts. So this is my answer. Right, so I have answered this question. What is the power across the 20? Now I can add more questions if I want to. For example, what is, let's say, the voltage across this one? What is the voltage? Well, the voltage here, the initial voltage is obviously 20. There is drop voltage here, so I can find what is the voltage, and it will be the same for everyone because they are parallel. I can do that. So the voltage across 30 will be, so let's find the voltage here. The voltage will be this resistance times the current, which is 0, 2, 8, and 6. That's the voltage across the 40. So what is it? 0.286 times 40. So 11.4. So this is 11.4 volt. So the source is trying to raise the voltage from 0 to 20 volt. There is a drop across the 40 ohms. What does it mean? Particles will lose energy because of this hill. And so here you will have then the voltage equals 20 minus 11.44. So minus 20 equal 856. So this is 856. And so this voltage is the same here and here. Why? Because they are parallel. So this is the same voltage. Now I can find the current here in every branch. The current in 30, let's get I30. What is it? And everyone is the voltage over R. Happens to be the same. The voltage is 8.56 divided by R30. So what is it? 8.56 divided by 30 equals. So 0.285. Okay, so there is small amount going here, here, and here. This current will be split in 3 ways anyway. Right? Yes, alright. So this is the current in every. The power will be V square over R. The power across 30 will be Ri square or V. So that is 8.56 squared over R, which is 30. Alright, so let's do it again. So I have 40 times 0, 1, 2, 8, 6. Yes, 1141 minus 20, 856. Alright, so 856 squared equals divided by 30, 2.44. Alright, so times 3. Alright, okay, so in this small exercise, so we're able to do a lot of things. Find the total current leaving the source, the power dissipated in the 20 ohms, the voltage across 40, the voltage across each one of them, which is the same, 856, the current in each, which is 0.285, and also the power across each these resistors in parallel. So this is the kind of analysis I expect you to do during the exam if you have only one source. So the first thing to do is reduce the circuit, find the total current, and then go back to the initial one and follow the picture. If you have two sources, then you will have to use Kirchhoff. I will do another video.